Hi, and welcome back to The Joy of Ray Tracing, a video series in which we make several ray tracers from scratch. On the last episode, we had just started making our very first ray tracer, and we learned how to loop over all the pixels on the screen. We then took each of those pixels and colored them based on where they were located on the screen. Now in today's episode, we'll be taking a look at the topic of vectors and how we can use vectors to represent all of the rays that will be shooting out of each pixel for our ray tracers. Also, we'll see that vectors come in really handy when we want to position objects in the scene that we want to ray trace. So let's take a look at what we're going to do today. Today's to-dos. First, we'll take a look at what are vectors and why we need them to do various operations in our ray tracers. Next, we'll take a look at how we can perform some basic operations on vectors like adding, subtracting, and scaling. Then we'll take this knowledge and start coding our own tiny vector utility library in JavaScript. And this will help us with all the vector operations that we need for our ray tracers. And then right away, we'll use our new vector library to create a ray for each pixel on the screen. Now, if you recall from last time, we still had the screen coordinates as being 0, 0 in the top left-hand corner, all the way down to the bottom right-hand corner, which was canvas width and canvas height. But for our future ray tracers, we need the notion of the origin, or 0, 0, being right in the middle of the screen. And this small change to our coordinate system, making 0, 0 the center of the screen, will help us later on down the line when we want to add a camera to our ray tracers. And as you know by now, I like to do at least a little graphics programming on every episode. And so once we've used our new vector library to create all the rays for each pixel on the screen, then we'll color each of those pixels based upon which way its ray is pointing. So let's get started. First, let's take a look at what vectors are and how they're defined and how we can use them in our ray tracers. Now, with any new topic like this, I always like to go back to the beginning and start with the basics so that no matter what your background is in computers and math, that you can follow along with us and fully understand what we're doing when we write our ray tracers. So to help explain the topic of vectors, I'm going to go into my whiteboard app here. And if you'll allow me, we're going to go all the way back to when you were 6 or 7 years old in grade school and you learned about this thing called the number line. So here I've drawn out a small example number line that hopefully most of you will recall. And the reason that I'm starting with this simple number line is because vectors can be of any dimension. So typically in ray tracers, we use 3D vectors or three-dimensional vectors that have X, Y, and Z components. But actually, you can have any number of dimensions for your vectors, and why not start off with the simplest case of a vector in one dimension, so that all we have to worry about on this first board is one dimension. So as you were taught in grade school all those years ago, every number line has an origin, and the origin is usually reserved for the number 0. So we call this point the origin. And as with all number lines, we have these little tick marks at evenly spaced intervals to the right and to the left of the origin. And most of our day-to-day math is based on this simple number line. So when we count items or do simple addition and multiplication, it's all based on this 1D number line. So how do vectors fit into this system? Well, the notion of a vector comes from the more general study of linear algebra in mathematics. And although it may sound scary to say we're going to be using topics from linear algebra, don't worry, because as you'll see, to do computer graphics and to do ray tracing in particular, we only need a very small subset of vectors from the world of linear algebra. And so what is a vector, you may ask? Well, a vector is a quantity that has both length and direction. And so when I think of vectors, I think of tiny little arrows pointing in different directions in space. So let's go to our simple 1D number line here and create our first vector. So I'm going to start at the origin and I'm going to go up to 4. And so you can see our vector here drawn in a light red color that is pointing in the positive direction. And so we call this part of the vector the tail. So that's where it starts, that's its origin. And then we call this part the tip, that's the arrow. And so remember what we said about vectors, they have both length and direction. You can't have a vector unless you have those two bits of information. So we can see right away that this vector is pointing to the right or in the positive direction. And so it has direction and then it also has length. So you can treat it like a line segment and just figure out how long it is simply by counting. So we start at 0 and we go all the way till we get to the tip of the arrow. So we start 0 and count 1, 2, 3, 4. So this vector has a length of 4. And just like in most objects in math, you can put a name on this vector. And so we can call this vector v. And usually you put a little arrow over the letter to denote that it's a vector. So now we can say that vector v is of length 4 and it is pointing to the right. And although this may seem overly simple at this point, we're going to define a way to calculate the length of a vector. And so we're just going to write a little formula. I'll use my purple pen here. The length of a 1D vector equals the end of the vector, where you ended up, minus the start, where you started from. And also, I'm going to put these special bars in pink around this simple equation, and that means the absolute value. So when you're talking about the length of something, it doesn't make sense to have negative length. So when we're calculating the length of a vector, we only need to know the magnitude of that vector, how far we walked along the number line. It doesn't make sense to have a negative length of something. So let's take a look at our little red vector down here and see if we can calculate its length. Now in this example, it's trivial because we started at the origin and you can just simply look at where it ended up, and where it ended up is 4, so you can guess it's 4 units in length. But I wanted to start off simple here because when it doesn't start at the origin, then this little equation here will come in handy. So let's take a look at the red vector and you do end minus start. So where did the vector end up? Well, it ended up at 4. So I'm going to write 4 minus, and where did it start from? It started from 0. So 4 minus 0 equals 4. So now we have determined that this vector has a length of 4. and it's pointing to the right or positive direction. Now let's create another example vector. I'll name this vector u. And again, we put a little arrow over it to denote that it's a vector. So now we see that the vector is pointing in the opposite direction, so it's going negative now. And so if we wanted to calculate the length of this vector, we use the exact same equation. And this is when the absolute value part of it will come in handy. So let's take our equation, which says we use the end minus start. So where did the vector end up? It ended up at the number -2. So I write that first. Minus the start. It started at the origin again, so that's just 0. And now we have -2 as the length. But recall, we don't really want to talk about negative length. That doesn't make much sense. So we take the absolute value of this -2, and that equals +2. Now we can say vector u is of length 2, and it's pointing in the other direction, which is negative, from the first vector that we had, which was vector v. Let's do one more example on this simple 1D number line, and then we'll move on to 2 dimensions. And I'll call this one vector s. So now my question to you is, what is the length of this vector? We can clearly see it's pointing in the positive direction, but now this is when this little equation comes in handy, because vectors don't always start at the origin. But all we have to remember is this simple phrase, end minus start, absolute value. So let's use that to calculate the length of the vector s. So now, where did it end up? It ended up at +4. So I'm going to write +4 minus, and then where did the vector start from? Well, it started at -3. And typically in math, when you have a negative minus something that's negative, you put that negative in parentheses. So -3. And as you learned in grade school, when you have 2 negative signs, that equals a positive. So it's actually 4 plus 3. And that equals 7. So now we say the length of vector s is 7 units, and it is pointing in the positive direction, or to the right. So how about we jump up to the next dimension now and try some vectors in 2 dimensions. Okay, so you see that we have the old number line from the previous whiteboard, which was a horizontal number line that went from left to right, or east and west. But now we've added another number line that goes up and down, or north and south. So when you add this second number line to the first number line, you get what is known as a Cartesian plane, or a Cartesian coordinate system. Pretend you were looking down on this as a flat sheet of paper, or like a large map. You can get to any point on the map by walking along the horizontal number line a certain distance, and then walking along the vertical number line a certain distance. So you can reach any point on this flat infinite plane by just specifying two coordinates. And when we have two number lines like this, we usually refer to each number line as an axis. So the horizontal number line is usually called the x-axis. So I'll write that over here. And I'll use another color for the vertical number line, and we usually call that the y-axis. And furthermore, if we go in the positive direction on an axis, we usually say we're going along the positive axis. So we'll call this the positive x-axis. And if we go this way on the x-axis, we'll call it the negative x-axis. And similarly, if we go up the y-axis, we're going along the positive y-axis. And if we go down the y-axis, we're going along the negative y-axis. The origin is where both number lines intersect or meet. So at the 0 location along the x-axis and the 0 location along the y-axis, where they meet is called the origin. So now that we're living in 2 dimensions on a flat sheet of paper or like a map, we can have vectors that kind of wander off the x-axis, and their movement is not limited anymore by that 1D number line that we had on the last whiteboard. So I'm going to use my yellow color here, and I'm going to make a vector that goes like this. Let's give a name to this vector. So once again, I'll call it V. Put a little arrow over it so you can tell it's a vector. And the 2D coordinates for this vector are going to represent how far we had to walk along the x-axis and how far we had to walk along the y-axis. So I'll use my red color now, and let's make a vector in red that goes from the origin, but just along the x-axis. And then I'll use my green color, and likewise we'll make a vector that goes in the vertical direction that represents how far we had to walk in that direction. Now this red arrow can represent the x-coordinate of vector v, and then the green arrow will represent the y-coordinate of vector v. So now we can write vector v as a coordinate pair. So hopefully you can see the coordinate 4 comes from the length of the red vector along the x-axis, which is 4, and then the 3 comes from the length of the green vector along the y-axis. Now, what if I were to ask you, what is the length of vector v? Well, now that we're in 2D, unfortunately, it's not as simple as the 1D case where you could just do a simple subtraction, but we can use the famous Pythagorean theorem to help us get the length of this 2D vector that can be pointing in any direction. So watch what happens when I take this green arrow and I move it over. Now I've created what is known as a right triangle. Right here we have a 90-degree angle. And if you've sat through trigonometry class in high school and were wondering to yourself, when am I ever going to need this? Well, here's the moment where we need it. So now that we have a 90-degree right angle triangle, we can label each of the sides of this triangle with a letter. So let's call this side A. And then let's call the vertical side B. And let's call this side C. These are simply the sides or legs of the triangle. So we have leg or side A, side B, and then this special side is always the longest side of a right angle triangle, and it is called the hypotenuse. So basically what we're trying to find when we want to ask what is the length of vector v, we're trying to find the hypotenuse of this right angle triangle. And so we turn to Pythagoras, and his theorem states that a squared plus b squared equals c squared. Now I'm going to take this simple equation and just reorder the terms slightly so that the c squared is on the left side of the equation. I'm going to use my colors that represent the colors of these vectors. So c squared equals a squared plus b squared. So all I've done is just flip around the terms on each side of the equation. So now we have the c squared over here, and then the a squared plus b squared is over here. And now our job is to solve for c. So what we can do in this case is write c squared equals, so what was side A, which is in the red color, was 4. So we write 4 squared plus, and then what was B, that's in the green color, so that was 3. And so we write 3 squared. Now we just need to simplify and we'll get our answer. So c squared equals 4 squared is 16 plus 3 squared is 9 . 16 plus 9 is 25. And now finally, to get rid of this squared exponent, we can just simply take the square root of each side of the equation. So that looks like this. Square root of c squared equals square root 25. And now when you take a square root of a square, those cancel. And you're left with c equals the square root of 25, which is 5, because 5 times 5 is 25. So the final answer is a length of 5. And now we can write vector v has a length of 5, and it points in the northeasterly direction. So before we move on to operations that we can do with vectors, let's take a look at how we write out the components of a vector. So here we have our 2D plane or 2D Cartesian coordinate system, with the x-axis going horizontally and the y-axis going vertically. And suppose I had a vector like this. How would we specify that vector? So typically when we use vectors like this in a geometric fashion, we assume that their tail, or where they start, is always the origin of the coordinate system. So you can see that the purple vector here has a tail that starts right at 0, 0 in the coordinate system. And so to specify this vector geometrically, we can just write its coordinates. So how far do we walk along the x-axis for the first number, and then the second number of the coordinates is how far we had to walk along the vertical axis. So in this case, we could just specify this vector as 2, 1. And the 2 represents the length along the horizontal axis, and the 1 represents the length along the vertical axis. Another way to put it is these are the x and y coordinates of where the vector ended up. Its final destination was 2, 1. That's where the arrow tip is pointing to. Let's just try a few more so we can get used to naming the components of the vectors. So this time we see the vector is kind of pointing in a northwesterly direction. So we had to walk along the x-axis 2 units, but we went in a negative direction. And then we had to walk along the y-axis in a positive direction again, but now we went 3 units up. So now if we want to write the components of this vector, we write it as x, y. So what is the x component? That's simply -2. So we write this vector as -2, and then how far do we go up the y-axis? We went 3, so 1, 2, 3, and we can write 3. Let's do one more and I think we'll have the hang of it. So recall, vectors can point in any direction in 2D, as long as they stay in that 2D plane. Now we see this new purple vector is going in a southwesterly direction. It's going to the left and down. And so there's nothing that says the components have to be positive all the time. So in this case, we're going to have negative values for both the x and the y components. So we always do the x-axis first. So how far do we have to walk along the x horizontal axis? So we did 1, 2, 3, 4, but it's a -4. So now we write -4 first, comma, and then how far do we go along the vertical axis? So we did 1, 2, and again it's -2 because we went down. So -2. And that clearly defines this vector's location of the arrow, of the tip of where it landed, of where it ended up. And again, this only works if the start of the arrow or the tail starts at the origin, or 0, 0. So you can see here that the tail started right at 0, 0. And then we can view this as pointing to a location on the grid. Now, if that tail didn't start at 0, 0, you can no longer say it points to a coordinate, because these numbers here, this -4 and -2, only makes sense at pointing to a coordinate on the grid if the tail is 0, because it's kind of like an offset from the 0, 0 location. So if I were to physically take this arrow, this vector, and move it around the graph, let's say here, mathematically speaking, it's still -4, -2. So we would have to take this definition as well and move it up and specify this vector as -4, -2. So in this instance, it just means how far did you go along the x-axis from the origin of the vector, or the tail of the vector. So we went from the tail and went in a negative direction for 4 units. And then we went from the tail down 2 units in the vertical direction. So these two numbers always specify an offset from the vector's own tail, or where it started from. So you have to find the origin of the vector, and then these numbers tell you which way to walk and for how far to walk in that direction. Now, in our ray tracing programs, when we use vectors, typically we'll put the vector starting at the 0, 0 location so that their tail is right on the origin. And that way, when you specify numbers like -4 and -2, they mean something more than just an offset. They actually can represent a location, if you like. So now let's take a look at some basic operations that we can do with vectors. Let's create 2 new vectors. Okay, so now I have 2 vectors, and let's name the red vector U, and that has a little arrow over it, remember? And then the green vector we'll name V. Now the question is, can we do something like this? So does it make sense to add vectors together? And the answer is yes, we can actually add these 2 vectors together. So going back a step, if you take 2 numbers, let's say 2 and 3, and you add them together, your result will be another number, like the first 2. So 2 plus 3 equals 5. And so 5 is in the same category as 2 and 3. They're all real numbers on the number line. But now when you have 2 vectors, when you add those together, your answer will be another vector. And it will have as many components as your original vectors did. So if you have these 2D vectors, they have 2 components. So they have an X component and they have a Y component. And so when you add those 2 together, you're going to get a new vector with an X component and a Y component, just like your starting vectors. So let's take these 2 now, U plus V, and the good news is it's the same way you learned in grade school to do addition and subtraction. So it's super easy. You just take the components of each and then add them together, and you get the new vector automatically. So the first step is labeling vector U and labeling vector V as to what their components are. So how far in the x-axis did we go, and how far in the y-axis did we go, and in what direction. So let's take the U vector first. So we went along the x-axis. We always do x first. So we went 1, 2. So we write down its coordinates or components as 2, comma, and then how far do we go in the y-axis? We went only 1, so 1. And now let's take a look at the green vector, vector V. So we do the x-axis first. So we walked over 1. So we write down 1 as the first component. And then for the y-axis, we walked up 1, 2, 3. So we write down a 3. Now, it's as simple as adding these two numbers together. So let's look back over at our equation, which is vector u plus vector v. And so that equals vector u, which is 2, 1, plus vector v, which is 1, 3, equals, and I'm going to use a new color here, yellow, to denote the new vector that we get out of this operation. So all you do is take the x component of vector u, which is 2, and add it to the x component of vector v, which is 1. So 2 plus 1 is equal to 3. So now we'll write 3, comma, and then likewise you do the same for the y components. So the y component of vector u is 1, and the y component of vector v is 3. So 1 plus 3 is 4. And now our result is a new vector, which is denoted by 3, 4. And let's draw that vector on our little graph here in yellow. So I walk 3 units to the right, and I walk 4 units up. So 3 units to the right and 4 units up. And now we can write the components of that vector again. So it's 3, 4. So again, all we did on this vector addition operation is just add up the individual components. So we took the first component of each vector and added them together. And then we took the second component of each vector and added those together. And we simply get the sum of all the components. So that makes sense from a purely mathematical point of view, but geometrically, what does vector addition look like? And so for that, I'm going to move this 1, 3 temporarily. And to show this operation on a graph or geometrically, what you can simply do is start with the first vector. So that's vector u, and that goes to here. It ends at 2, 1. And then physically take the green vector and put its tail where the red vector ended. And look what happens. We ended up at the exact same place that the yellow vector did. So geometrically, you can see that when you add two vectors together, you get a third vector that is the same destination as if you were to walk along the two original vectors. If I was looking down on this like a map and I walked from the origin to the end of u, and then I walked from the origin of the green vector all the way to its tip, then I would end up at the same location as if I just walked straight along the yellow vector. I would end up at 3, 4, no matter which way I did it. And so another cool property of vector addition is that it is commutative. And that means that you can swap the order of the vectors that you add together. So vector u plus vector v is the same thing as saying vector v plus vector u. So going back to our 1D example of the simple number line, 3 plus 2 equals 5. But what is 2 plus 3? Well, that's also 5. So it doesn't matter the order in which you do the addition. It doesn't matter which comes first and which comes second. So what does that look like geometrically, though? If you wanted to show someone a picture of this commutative property. So let's take the green arrow and move it back. Now, vector v plus u is like saying I walk along v and then I walk along u. So we put the tail of u. So let's take this and physically move it so that its tail is where vector v stopped, the green vector. And look at that, we end up at the exact same location. So in other words, if you walked along vector v to 1, 3, and then you walked this distance in the x direction, so 2 over and 1 up in the y direction, you land on the same exact coordinate as if you simply walked along the yellow vector to 3, 4. So in your mind, if you put this green one first and then the red one next, it would be 1 plus 2 equals 3. And then 3 plus 1 equals 4. So it doesn't matter which order you do them in. It's commutative. Now let's take a look at vector subtraction and what that means. So again, here we have two vectors, one red vector and one green vector, and let's name these again u and vector v. And the components of vector u are simply the coordinates where it ended up. So it ended up at 4, 1, and the green vector ended up at 1, 3. So now, does it make sense to subtract one vector from the other? So if I wanted to do something like this, vector u minus vector v, is that possible? And does it make sense geometrically? Well, the answer to both questions is yes. So just like you learned in grade school to subtract numbers, so 5 minus 3 equals 2, then you can do that with vectors as well. So we simply take each component of the vectors, the x components and the y components, and we just subtract those. So let's rewrite this as vector u was 4, 1 minus vector v, which was 1, 3. And so now just start with the x components. So the u has a 4 for the x component, and the v has a 1 for the x component. So we just take those two numbers, 4 minus 1, and that equals 3. So again, I'll use my yellow color here to denote the new vector that we get from this operation. So 4 minus 1 is 3, comma, and then take the y components and subtract this one from this one. So now in this case, it's going to go negative because 1 minus 3 is negative 2. So, and that's perfectly fine. So our new vector now, as a result of this operation, is 3 comma negative 2. So let's draw that on the graph. And we can write its components beside it, where the tip of its arrow ended up. So we write 3 comma negative 2. And geometrically speaking, that means we walked to the right 3 units, and then we went negative 2 in the y-axis. So that means we went down 2 units along the negative y-axis. And so we saw mathematically what this accomplishes in giving us a new vector from the subtraction operation. But what does this mean geometrically? Again, I'm going to move the components of this vector over just a little bit. And now take the yellow vector and physically move it so that its tail is on the green vector where the green vector ended up. And look at that. It directly connects both arrow tips. And so its tail starts at the tip of vector v and then continues and it ends up at vector u. Now this was why I was talking about the origin of the vector matters, because you could look at this and go, oh, that's 4 comma 1. Well, that's not correct, because the numbers that you put in these parentheses represent how far you walked along from its own tail. So if you start at this tail, then you have to use these set of numbers here. And so we have to grab this and move it up here. So even though those two vectors point at the same coordinate of the grid, they don't have the same components. Quite the opposite, actually. So this one has a negative y component, whereas this one has a positive y component. That's because the red vector is going up, so it has a positive number here, while the yellow vector goes down, and that's why it has a negative number. This little fact here might be confusing because you see the same point on the graph, but they're two different sets of components. But I just wanted to show you that there is a geometric interpretation of vector subtraction. Now, as you learned in grade school, subtraction is not commutative. So that means that you can't swap the order of the numbers that you're subtracting. So 5 minus 3 equals 2, but 3 minus 5 equals negative 2. So it makes a difference which order you put them in. So therefore we can write vector u minus vector v is not equal to vector v minus vector u. In fact, it's the opposite answer. So 5 minus 3 is 2, but 3 minus 5 is negative 2. And so it's a negation of the result. So finally, we could say vector u minus vector v is equal to the negative result of vector v minus vector u. But the thing I just like to remember is that you can't swap the order of a subtraction operation, but you can when you're doing addition. So you can put them in whatever order you like and you'll end up with the same answer. All right, now let's move on to the idea of multiplying a vector by a scalar number. So much in the same way as you can multiply two regular numbers together, like 2 times 3 equals 6, you can also multiply the components of a vector, its x and y components, by a number. So let's go back to our graph and see what that looks like visually. So I'm going to create a vector with the components 1, 2. So now let's say I wanted to scale this vector. And essentially scaling means you stretch the vector or squash the vector down. And so let's try scaling it up or stretching the vector. And we'll see what that does visually in a moment. And we'll call this vector v again. And what we're asking is, does it make sense to scale vector v by a number? We'll represent this scalar number as a letter of the alphabet, so I'll just use a, lowercase a. So what does it mean to scale a vector v by a number a? And so essentially what that means, mathematically, is you take the components of v. So in this case, we had 1 as its first component, and then you just simply multiply it by whatever your a is. And then take the second component, which was 2, and multiply that by the same scalar number. So now to do an example, let's scale this vector v by 2. So our equation now becomes vector v 2 equals the first component times 2 and the second component times 2. I'll draw the result in a bright purple color. So you take the first component, 1 times 2, and that simply equals 2, comma, and then the second component is 2 times 2, which is 4. So much in the same way, when we were adding and subtracting vectors, we did a component by component operation of that type. To scale up or down a vector, we simply take the scalar number and apply it to all of its components. So in this case, the vector lives in 2D land, this flat plane, and so its x component gets multiplied by the blue number here, the number 2, and its y component also gets multiplied by that blue number 2 there. And we end up with a new vector with these components. So now let's go and draw this vector and see what it looks like. So I'm going to use a purple color. And I'm going to go to 2, 4. And we can also label it with its components 2, 4. So now looking at this geometrically, what can we say? Well, the purple vector is pointing in exactly the same direction as the red vector. And also, it looks like it's about twice as long, which it is. So if you multiply 1 times 2, you get 2. And if you multiply 2 times 2, you get 4. And so this purple vector is a double of this red vector. It would take 2 red vectors to get to this purple vector. So we've essentially stretched it by 2. The important thing to remember is if you do any kind of scalar multiplication like this, you never change the angle or slope of the vector. In other words, how steep or flat it is. You can only change the length of the vector. So now let's try another scalar multiplication, but this time we're going to shrink the vector. So my original red vector will have the components of 4, 4. And now I want to take this vector and scale it by half. And we can write that as a decimal 0.5. So mathematically, that simply means we take each component of the vector and multiply it by 0.5. So that's 4 times the scaling factor of 0.5, comma, and then 4 again for the y component times the scaling factor of the same 0.5. And then once more I'll use the purple color to denote the new vector. And 4 times half, or half of 4, is 2. So we write 2, comma, and again the y component is the same, 4 times 0.5, which is 2. So we end up with a new vector pointing towards 2, 2. And so let's draw that in our graph so we can see that. So again, starting at the origin, I'm going to go to 2, 2. And once more, you see that we have kept the direction of the vector, the scaled vector, exactly the same as the direction of the older vector. So nothing has changed in terms of how steep they are or what their slope is. But as you can see, it would take 2 purple vectors to get to a red vector. So the purple vector is exactly half the length of the red vector. Let's do one more example and then we'll move on to the final topic for today, which is called normalization. Now, the reason I didn't say that scalar multiplication of a vector doesn't change its direction, and rather I said it doesn't change the steepness or the slope, is because, as we're about to see, when you multiply it by a negative scaling factor, it actually points in the opposite direction. So let's take a look at that mathematically first, and then we'll draw it out. So now I have this red vector, and its components are 3 in the x direction and 4 in the y direction. So I specify that by writing 3, comma, 4. And now what I'm going to do is take this vector v, let's name it v again, and multiply it by -1. And I'm going to put that in parentheses so it doesn't look like a subtraction of 1. So this is multiplying the vector by a scalar of -1. So now, as we've done before, we just take each component of the vector and multiply it by -1. And so here's what that looks like. So 3 times -1, comma, and then 4 times our scaling factor of -1. And that equals, I'll use the purple color once more. 3 times -1 is -3, comma, and then 4 times -1 is -4. So mathematically speaking, we started out with 3, 4, and now by multiplying it by -1, we ended up with the exact opposite, which is -3, -4. So let's go graph that and see how that looks. So I'm going to walk over -3 this way and -4 down. And now what can we notice about this new vector and how it relates to the old vector? Well, for one thing, they're both the same length, it looks like to me. So in fact, they are the same exact length. And the purple vector is exactly parallel to the red vector. So if you were to draw a line, you could exactly draw a line through both of these vectors, and it would be on the same exact line. The only thing that has changed now is that the red vector was pointing up and to the right, and now the purple vector points the exact opposite direction, so it's down and left. And so now we can write the components down here, -3, -4. And in particular, this operation of multiplying by a -1 and keeping the same length and just reversing the direction is called vector negation. So just like we have a negation of a number, so 5 times -1 is -5, we can also have the notion of a vector pointing in a certain direction and then negating it so it points the exact opposite direction, but it remains exactly parallel to the first vector. Now, before we get to our last topic, which is vector normalization, you might have noticed that I kind of skipped over the multiplication of two vectors. So in other words, what does it mean to multiply vector u by vector v? And when I first thought about this many years ago, before I knew about vector products and things like that, I thought, well, since the addition of two vectors and the subtraction of one vector from another simply meant that you just take each component and do that operation and you're left with the answer, why can't we just take the x component of the first vector and multiply it by the x component of the second vector and then do the same for the y components? But in reality, that doesn't really mean much geometrically, and it is not an operation that is done in linear algebra. And remember, linear algebra is where we borrow all these notions of vectors and vector spaces from. So if you want to multiply two vectors together and get a product, which remember is if you multiply normal real numbers together, like 5 times 3 is equal to 15. So the 15 would be called a product of the two original numbers. And so if you wanted to get a vector product, then you actually have to do a little more work than just multiplying the x component times the x component of the other, and then the y component of the first times the y component of the second. So it's not quite that simple. And there's a couple ways you can do a product with vectors. And one is called the dot product, and the other is called the cross product. And so we will discuss those in a future video. Maybe on the next video, I'll talk about the dot product and how we do that, because that's pretty simple. And then the cross product is just a little more involved, but we will cover that in a future video as well. So now let's talk about our last topic today, and that's called normalization. And so when we talk about normalization, that means taking our vector and no matter what length it is, scaling it so that its final length is exactly 1. And for now, let's zoom in on this coordinate system and just draw a couple of vectors that are of length 1. And when they have a length of 1 exactly, we call them a unit vector. So unit vector means it has exactly a 1 as its length. So let's draw a red vector in the x direction. And so if we were to write the components of that vector out, it would be, we walked 1 over to the right, so that's 1, comma, and then how far do we go up? Well, nothing, so that's 0. And remember, going back a few moments when we did the calculation of a length using the Pythagorean theorem, if you were to actually do the Pythagorean theorem on this set of components, you would get exactly a length of 1. And that makes sense because it doesn't go in this direction at all. It doesn't go up or down at all. It just goes to the right, exactly 1. So it has to be a length of 1. That's all it can be. Now let's do one for the y-axis that goes up. So I'll use a green color for that. And if we were to write the components out for that vector, well, we do the x component first, and we didn't move at all in the left and right direction, so we put a 0 for that. Comma. And then how far did we go in the vertical direction? Well, we went 1 positive, so that's positive 1. And so its components are 0, comma 1. So now we have two vectors that are both unit vectors. They have a length of exactly 1. And if you did the Pythagorean theorem on them both, they would come out to be exactly 1. Now you may or may not remember from your geometry class that we have an idea of a unit circle. And so a unit circle has a radius of exactly 1. So let's put a circle down here and see how that relates back to our vectors. Okay, I'm still learning this OneNote program, so you have to bear with me. It took me a while to get that purple circle there. Okay, so this purple circle is called a unit circle because in every direction, no matter where you walk out 1 unit in length, and then you reach the edge of the circle. So if you start at the origin and go in this direction, you walk exactly 1 unit of radius. Likewise, if you go in the north direction along the green arrow, you again walk for a length of 1, and then you reach the circle. And you could go in the left direction, you could go down, you can go diagonally. So it doesn't matter which direction you go in, but the radius has to be 1 everywhere. So when looking at the red vector and the green vector, those were already given to us as unit vectors. They already had a unit length of 1, and they were already located. Their tips were already on the purple circle. But now I'm going to zoom back out, and let's say we're given a random vector. So I'm going to draw that one in pink. So its components are 3 in the horizontal direction and 4 in the vertical direction. So 3, 4. Now obviously this is not unit length, but there comes times in computer graphics when we're only interested in the direction of a vector, which way it's pointing. We don't care at all about how long it is or how short it is. So in those cases, we want to shrink the vector down to match the unit circle, which is in purple here. We want to essentially shrink this pink vector down so that its tip is on the purple circle boundary. And likewise, if this pink vector was really tiny, like over here where my mouse cursor is, we would have to expand it a little bit so that it came out to reach the boundary of the circle again on the purple line, the purple circle. So essentially what we need is a scaling factor, and we just learned how to scale vectors. Remember, we changed their length, but we didn't change the direction. And remember, we care only about the direction in these instances where we have to make it a unit length of 1. And so we don't want to change the direction at all. All we want to do is either shrink or expand the vector. So here's the process that we have to do. First, we find the length of the original vector. Oh, and I'll call this vector v again. And remember from a couple of whiteboards ago, we learned how to do that using the Pythagorean theorem. Once you find the length, you divide each component of v by that length. And I'm going to put a couple of vertical bars around this v. So this equation essentially says the version of vector v that is unit length is equal to the following process. And so this process is called normalization. And so we're normalizing the vector v. So we're taking it can be whatever length you want, but we're either shrinking it or expanding it to exactly match that little purple circle that's of radius 1. And when it's that exact length of 1 inside that unit circle, then we can say it's a normalized vector or a vector of unit length. There's a bunch of words for it, but it all means the same. And if we take the first component of vector v, that's 3. And so we take 3 divided by whatever length we found v to be. Let's say if the length was 6, I'm just guessing, we're going to actually calculate it in a moment, but you would do 3 divided by 6, and then you take the second component, 4 divided by 6, which is the length of v. So we're going to find out now. And I just realized that I made a vector that's going to be a 3, 4, 5 triangle. So, but we'll do the math anyway, just so you can see it one more time, even though that we know what the answer is going to be. So, and I'll use the same colors as I did on the previous whiteboard. So c squared equals a squared plus b squared. Three squared is 9. That's a squared, which is 3 squared, which is 9. And then b squared is 4 squared, which is 16. And then we have c squared equals 25. And we take the square root of both sides of the equation to get rid of that squared exponent. And then as we saw previously, c is equal to the square root of 25, which is 5. And now, where we have length in this equation, we just replace it with the number 5. So now that becomes 3 divided by 5, comma 4 divided by 5. And now we can say that the normalized version of vector v that has unit length is equal to 3 over 5, so 3 divided by 5, or 3/5, comma 4 divided by 5, or 4/5. Remember that we can't have anything longer than a length of 1. And so the maximum you can have in either component is 1, exactly. If like the x component is 1, then the y component has to be 0. And if the y component is 1, then the x component has to be 0. So you can never have like 1 and 1, because that would be longer than 1 when you drew that out. And so all these unit vectors that are of length 1 will have components that are at 1 or less than 1. And oftentimes it's the latter case where it's less than 1. So you'll have like a fraction or a decimal like 0.72 or 0.267 or something like that. So it'll never be over 1 in any component. And now if we went and graphed that, that's why I drew the purple circle, because now I don't have to like count fractions on my graph here. Let's let's move this all down here so my camera doesn't get in the way. Okay. So now we want an x component of 3/5 and a y component of 4/5. Now, off the top of my head, I can't do that very well, but I know that it must lie on this purple circle somewhere. And since we started with the pink vector v that went in this exact direction, remember we never change the direction when we normalize. So now I can just shrink it down until it touches the purple circle. And I'll use the yellow color to draw our normalized vector. And now I'm going to trust that this unit circle is correct. And so I'm going to write the components of this vector as 3/5, which is less than 1, and 4/5, which is also less than 1. But just know that if you were to do the Pythagorean theorem on this set of numbers, it would come out to be exactly 1. And so this whole process was in order to get this pink vector, which was really long and unwieldy, and make it into something useful so that it lies somewhere on this purple unit circle. And now we can talk about that new yellow vector as a pure direction. So we no longer, we're just assuming that it's length of 1, so we don't care about its length anymore. All we're interested in is which way the arrow is pointing. Is it pointing up? Is it pointing down or right or left or diagonally? So that's all we're concerned with when we normalize a vector. And so later on in our ray tracing programs, there'll be times when we have vectors on a surface, like a curved surface, like of a sphere, and there's a vector pointing out of that surface, and we want to know exactly which way that vector is pointing. And it has to be really accurate, otherwise the lighting won't look right, because you take that little vector and you do calculations based on where the light is in the scene. And so if that vector is pointing at the light, it'll be brighter, and if the vector is pointing away from the light, it'll be darker. And so we'll take a look at that in future episodes when we actually start doing our lighting calculations on our objects in the scene. So how can we use these vectors that we just learned about to represent all of the rays in our ray tracers that we're going to be writing? Well, let's take a look at the components of a ray and what it means to be a ray. So a ray has 2 vectors in it. So there's one vector for the origin, and there's one vector for the direction. And so when you talk about a ray origin, that's a vector. And then when you talk about the ray direction, that's also a vector. So you need no less than 2 vectors to represent a ray. And if you were just to draw a picture of a ray, you might put the origin somewhere as a dot or a point in space. And remember, a mathematical point or an origin like that doesn't have any dimension. So although you can see the dot, in actuality, it's infinitely small. So it just represents a location in 2D space or 3D space when we get to actual ray tracing that's in 3D space. So we have a pink dot here representing the ray origin where it starts. And then we have to add to that a yellow vector in the direction that you want the ray to point. So let's take this, that's why I left this yellow vector here. Let's use this yellow vector as the ray direction. So I'm going to draw something like that. Okay, so now we'll call this ray R. So ray R. And maybe we can do a dot with an arrow showing that it has an origin and a direction. And so ray R has an origin of this pink dot right here, and it's also having a direction of this yellow vector. So if we wanted to make this yellow vector right here into a ray, it would be pretty simple, right? Because the origin is already at 0, 0. So we would just say that the origin for that is 0, 0 plus the direction. So 3/5, 4/5. And when you add those two vectors together, you get a notion of array. And I use this yellow vector on purpose because usually when we talk about rayDirections, we don't care about the length at all. So all we care about is the direction that it's pointing in. And almost 100% of the time, our rayDirections are going to be all normalized or unit length of 1. And so typically you'll see numbers less than 1 in the components for the direction vector. Now the origin vector can be anything you like. So the nice thing about having a normalized direction vector is I can physically take this yellow arrow and move it about. And then if I want it to be array, it needs an origin. So I'm just going to put the origin right at its tail in pink. And so now my array has an origin of a different location, and that's denoted by -3 along the x-axis and then -3 along the y-axis. So we would write it like this, -3, -3. But it's pointing in exactly the same direction. So we just write 3/5, 4/5. And that little yellow direction vector is still unit length, so it's a length of 1. But we're only interested in which way it's pointing. And on the pink vector, which is the origin of the ray, we never normalize that because we want to know how far from the origin of the world do we travel to get to this origin of the ray. So in other words, if we started 0, 0 on the graph, this -3, -3 represents how far we had to travel along the x-axis and the y-axis respectively to get to the new ray origin. And then we draw a dot there, and that's where the ray starts. And then we just tack on the ray direction, which we always know is unit length of 1. So it's confined to be like a little unit radius circle around that little origin. So it can be, this yellow arrow can point in any direction it wants to, but it has to remain on that little imaginary purple circle like we had over here. And so basically that's what array is, mathematically speaking. And geometrically, you can see that it needs 2 vectors. So one for the origin and one for the direction. So as long as you have 2 vectors representing your rays, you can have rays anywhere in your scene and pointing in any direction you like. But as you might have noticed, we haven't really talked about the 3rd dimension yet. So we've only been discussing things in 2 dimensions, so X and Y. But when we get into ray tracing proper, we have to consider the 3rd dimension, which is depth. So we have a notion of 3 different number lines now. So we have the horizontal number line, which is the x-axis, and then we have the vertical number line, which is the y-axis, and then we have one pointing out of the screen to you and away from you, and that is called the z-axis. So the bad news is we have to add that into our code when we start coding all this up and making a vector library. The good news, though, is that all these things that I've been showing you, they all work automatically with adding a 3rd dimension. So all you have to do in your code is just tack on one more component, which is the z component. So instead of x comma y, you'll have x comma y comma z. And you just tack that third one on there, and all the operations remain the same. So if you want to add vectors together of 3 dimensions, you just add all the x's, all the y's, and all the z's. And if you want to subtract, you subtract x from x, y from y, and z from z. And then if you want to scale the vector, you multiply the x times the scale factor, y times the scale factor, and z times the scale factor. And then if you want to find the length, you can use the Pythagorean theorem. And the beauty of the Pythagorean theorem is, no matter what the number of dimensions you have, the Pythagorean theorem still holds. So you can have 1 dimension, 2 dimensions, 3 dimensions, as we will use. You can even have like 57 dimensions. It doesn't matter. That little Pythagorean theorem, it all works no matter what number of dimensions you have. So that's part of the beauty of the Pythagorean theorem. That's partly why I haven't really talked about the z component, because it's something we can just tack on in the code. But to get a grasp of these new concepts like vectors and directions and length and things like that, it helps to start out in 2 dimensions and just get a firm understanding of that in 2D first before we try tacking on a third component, which is the z component, and bringing everything into 3 dimensions. So now that we know how rays are related to vectors and how we can use vectors to build up all the rays in the scene by having one vector for the origin of the ray and then one vector for the direction of the ray, let's go and start coding our own little vector library in JavaScript that we can use and reuse for our upcoming ray tracing programs. And as you'll see, hopefully, it's very straightforward to put all these simple equations and these vector definitions and vector operations into actual code that the computer can understand. And so let's go do that now. Let's open up Visual Studio Code. And here we see what we were working on last time. So we had just added this demo to our GitHub repositories, and that's a link for the pixel loop demo that we did last time. And so we can leave all these files up here. Click on the JS folder, and we're going to make a new file in that folder. Click on it a couple times to make sure you're in that folder directory, and then click on this new file icon. And since today's topic was dealing with vectors and vector spaces, which come from linear algebra, we're going to call this file math utilities, because it all comes from the world of math. So let's call this math utils, capital U, and that's short for math utilities, and then .js. And once again, you can see that this file name has turned green and it has a U beside it, and that means untracked. But as soon as we make a commit to this repository, that U and the green color will go away and the file will be tracked for our future use. So inside this mathutilities.js file, we're going to place a very small vector library. And the nice thing about having its own file like this math utilities, is that we can use and reuse it for our future ray tracers. So the first thing I'm going to do in this file is create what's known as an object constructor function. So when you call this function, it'll create a new object in JavaScript for you. So the way we do that is use the function keyword. Let's call the name of this function vector3, and vector3 stands for 3 components. Since we'll be dealing with 3 dimensions when we get into ray tracing, so we'll have an x and a y and a z component. This vector needs to have 3 components. And so we're going to just put that 3 into the name so that when you use it, you know that it works with 3 components all the time. And a constructor function like this always starts with a capital letter. So capital V vector 3. And now open parentheses, and it'll close it for you. And now what is it going to take as its parameters when you call this function? So remember, we said we needed 3 components, an x, a y, and a z. And so we're just going to place those in here. X, comma, y, comma, z. And then go on to the next line and type the opening curly brace, and it'll close it for you. Hit enter. Now I'm going to use the keyword this. So the this keyword in JavaScript refers to the object that this constructor function will make. So type the keyword this. We're going to add components to this object. And the way you do that in JavaScript is to use the dot operator. So type dot, and then we'll call it x, just like the parameters are called here. So this dot x equals, and we're just going to set it to x, whatever the user passed in when they called this function. And we end all statements in JavaScript with a semicolon. Now we just simply do the y and the z in the same manner. So type the keyword this dot y equals y. This dot z equals z. And after this function gets done creating this object with x, y, and z components, we just return this. So return this. Now there's one scenario that we need to handle, and that's if, what if the user calls this function and they don't put anything in the parentheses? So for instance, let's say they do this, let my vector equals new vector 3, and they decide not to put anything in there and they just leave it like that. Now my vector will be created as a new vector 3, but when it gets to this part of the code, it doesn't know how to handle this because the x and y and z parameters were not defined. So it'll put an undefined in those spots. So we need to handle that case where the user might not put anything in the parentheses when they call the constructor function. And a more recent addition to the JavaScript language is really helpful for that. And that is default values. So you can actually put default values up in the parentheses up here, and that way it'll take care of all those scenarios where the user might or might not pass in parameters to the constructor function when they call it. So the way you do that is x equals 0. And then you do the same for the y and the z components. Y equals 0 and z equals 0. So now if they use it in this manner, it'll just automatically default to zeros for all the x, y, and z components. And that way it'll know how to handle this line right here where it's trying to get the x and the y and the z. And likewise, if they do use the function as intended, so they can put 1, 2, and 3, it'll take that and assign those numbers to these components. So the new object, my vector, will get an x component, and that'll be set to whatever they passed in as the x parameter. So that'll be 1 in this case, and then 2 will go in the Y spot, and 3 will go in the Z spot. So that way we handle any scenario like that. So I'm going to take this out now. So this is our constructor function, vector3. And now how we give it functionality is we add to its prototype. So if we want to take this vector3 and add some functionality to it down here, we add on to its prototype. And it is how JavaScript handles putting functions and methods on objects like this. And so if this all looks a little unfamiliar to you, please go back and check out my JavaScript intro video back in chapter 0. And that gives a lot of examples and explains the prototype-based inheritance system that JavaScript uses. So now we've created this constructor function called vector3, and we can use that name now and add to its prototype. So vector3, and then you type dot prototype, and then it's going to take another dot, and then you put the name of the function that you want to add to its prototype. So let's make one called set. And so that'll allow the user or us programmers to set a vector to whatever components we want. So dot set, and then equals, and then function keyword, and then open parentheses, and it'll close it for you. And again, it's going to take an X and a Y and a Z parameter. So X, comma, Y, comma, Z. And this time we don't need the default values, because if a user calls this set function, they explicitly want to set the vector to X, Y, and Z components of their choice. So we can just leave it like this, X, Y, and Z. Now hit enter and open curly brace, and it'll close it for you, and then hit enter one more time. And now we get to copy and paste a little bit. So just take this, all these lines, copy and paste them in here. Because all this function does is take the X, Y, and Z and assigns those to the components of the vector that we call this on. And so this set function can only be called once you've used this constructor function. So once you've used the constructor function and created a new vector3, then you can call set on it and just set the components of the vector to anything that you like whenever you want. Now technically, this equal sign right here makes this a function expression. So since all expressions in JavaScript need a semicolon like this, or actually it's not required, but it's recommended, because you can get into trouble if you don't put semicolons after your statements in JavaScript. It can sometimes mess up the interpreter as it's trying to read through your code. So I like to put semicolons at the end of all statements and expressions. And so this one, this equals function, is kind of like a statement or an action. So you're assigning the function to the method set. And so we go after all this code and type a semicolon. Now technically you don't have to have that, but it's just good practice to show that this is doing an action and assigning a function expression. And now hit enter a couple of times. And again, we're going to add more stuff to the prototype of vector3. So once more, type vector3 dot prototype and see how it pops up. You can just hit enter when it pops up like that, and it'll fill it in for you. And then dot again to add to the prototype. So thinking about all the stuff that we would like our vector3 objects to be able to do, one useful thing that our vector3 could do is be able to copy another vector. So it just copies the x, y, and z components of that vector, and then it just assigns those to its own. So let's type copy, and that's going to be the method name, equals, and again we're using the function expression method here. So function, open parentheses, and now we're going to call this parameter other vector. So when you call the copy function inside the parentheses, you're going to specify the vector to copy. So other vector. And now hit enter. Open curly brace, enter. Now the body of this method is going to look a lot like this code here, but we're going to have to specify the other vector x, other vector y, other vector z here in this spot. So let's go ahead and just write that out again. I'm going to scroll up here so you can see better. So it's this dot x equals, now instead of just x, it's other vector dot x. So other vector, and you can hit enter when it pops up, dot x. And so it takes the other vector, whatever that may be, and then it goes and grabs its x component and then sticks it into our own x component. So it literally just copies everything from the other vector. And likewise, let's do the same for y and z. So hit enter, this dot y equals other vector, you can hit enter, dot y, and then this dot z equals other vector dot z. And once again, we'll return the newly set vector. So return this. And then this was a function expression. So once again, we should put a semicolon after this closing curly brace here. And then hit enter a couple times. So remember a moment ago when we were doing simple operations with two vectors. So we did adding, we did subtracting, and then on one vector we did scaling. So multiply by a scalar number. So let's add those functions now to be able to add vectors and subtract vectors and scale vectors. So now, once again, we type vector3 dot prototype. We're going to add to its prototype so that all vector3s have this functionality. And then we're going to call this function add. And then space equals, and it's a function expression again, so function keyword, open parenthesis. And just like this function, we're going to take the other vector as the parameter to this function. So other vector, and then now hit enter at the end of the line and open curly brace, enter. So remember from a couple of whiteboards ago when we were talking about adding two vectors together and what that means. You just simply add the x, y, and z components of each vector. So let's see what that looks like now. This dot x. And remember in JavaScript, we can kind of do a shorthand. Instead of saying something like x equals x plus 1, we can do x plus equals 1. So we'll do plus equals, and then use the other vectors x. So other vector dot x, and then type semicolon. So now it'll take the other vector's x and add it to this existing vector's x component, and then it'll save it back into this vector3 that we called it on. So when you call the add function, it adds it to yourself, basically. So you take a vector that you've created, and when you add another vector to it, it changes it by adding that other vector to your own vector that you had created. And then as you can guess, we do that for the y and z components as well. It's pretty straightforward. So this dot y plus equals other vector dot y, semicolon. And do it one more time. This dot z plus equals other vector dot z. And now return this. Now, since the next one is going to be very similar, let's go ahead and just copy all this and paste it below. So Control C and hit enter a couple times and Control V. And now we're just going to do a subtract function, and it'll do basically the same thing but with a minus sign instead of the plus sign. So change the word add to subtract. And then again, it takes the other vector. And now instead of plus equals, it's minus equals. So minus equals, and minus equals. Oh, and I forgot to add the semicolon to these. So let's add a semicolon to that and this one too. It's just one of those things where if you don't put the semicolon, it's not going to break your program. And I'm sure that I've written code before and published code that doesn't have the semicolons after these function expressions, but it's just good practice to try to stay consistent and put semicolons at the end of every statement or expression. Now go down just a little bit and hit enter a couple of times, and let's make a scaling function now. So we're going to multiply the vector times a scalar number. And so it'll take the x component and multiply it by that number, and then it'll take the y component of the vector and then multiply it by the number, and then finally the z component and multiply it by that same scalar number. So let's add that now. Vector3 dot prototype. And let's call this multiply scalar, because it's just going to take a scalar number and then apply that to the vector's components, the x, y, and z components. So multiply scalar. And then it's a function expression, so we do equals function, opening parenthesis, and then let's call the parameter scalar number so that it removes all ambiguity as to what goes inside the parameters for this function. So scalar number. And that way, hopefully someone won't accidentally put another vector in there and try to multiply two vectors. And remember, as we said, that doesn't make much sense geometrically. We will do that though for colors in the future. So when we get down to the lighting part of the ray tracing tutorial series and we're multiplying colors times each other, it helps to have the color as a vector 3, like RGB, and then be able to multiply two colors together. So R times R, G times G, and then B times B. But we will add that functionality later. Just for today though, we want the ability to take just a number and then apply it to all the components of a vector. And that's what we're doing here. So now hit enter and open curly brace, enter. This dot x times equals, and whatever the user passes in as a scalar number. So scalar number. And you can hit enter when it pops up there. And then let's do the same for the y and z components. It's fairly straightforward once more. So this dot y times equals scalar number, semicolon. And then finally this dot z times equals scalar number. And once again, we return this. So it returns the newly updated vector 3. Return this. Oh, and let's not forget the semicolon at the end of this function expression. Now these next two functions are not critical to a vector 3 library like this, but they're useful to have. So what I want to be able to do is have a function that takes a vector and floors all the components down. So it rounds down all the x, y, and z components to the nearest integer. It removes all the fractional components off of all the values for x, y, and z. And the other one will be absolute value. So once more, it'll take a vector 3 and it'll take its x, y, and z components, and it will make all those x, y, and z components an absolute value. So if they happen to be negative, then they'll turn positive. And if they're positive already, they'll just remain positive. So let's implement those two methods now. So the first one, vector3.prototype, and we'll call this floor. And that's simply, once again, that simply means just rounding down to the next integer and removing all fractional components. Equals function, opening parentheses. Now this is the first instance where we don't need anything as parameters because this floor function operates on itself. So we can go on to the next line and hit open curly brace, hit enter. And now we're going to set this .x to be the floor of this .x. And how we do that in JavaScript is to use the math object or the math library that comes pre-built in with JavaScript. So call the math, and that's a capital M, math object, and then dot floor. And you can see it pop up here. It says floor is a method, and it rounds down. The flip side of that one is called ceiling, so it rounds everything up. But the floor function to me is more useful. I like rounding things down to the next integer. So if you had like 1.672 or something, it would just take off the 0.672 and leave you with 1. So it's just a simple rounding down and removing of the decimal part of the number. So now that is a function or a method itself, so it takes its own parameter. So you type open parentheses, and inside the parentheses it tells you to put the number that you want floored. Well, we want this .x floored, so once again we type this .x. So it's operating on itself basically. And so now you can read this as floor this .x, and then we stick the result back into this .x. So it updates itself. And once again, hopefully you're seeing a pattern here. We're going to do the same thing for the y and the z components. So this .y equals math floor this .y. And then one more time, this .z equals math floor this .z. And once more we return this, which is the newly updated vector itself. Return this. I'm going to scroll down here a little bit. Oh, and let's not forget the semicolon. And then now go on to the next couple of lines here, and let's add a function called absolute. So vector 3.prototype, and we're adding on to the prototype once more. And let's call this absolute equals function, opening parentheses. And once more, we don't really need any parameters for this because it's going to operate on its own self. So it's going to take all of its x, y, and z components and just give you back the absolute value of those components. So enter, and opening curly brace, enter. This .x equals And once again, we're going to use the built-in JavaScript math object, or math library, as I like to call it. So capital M math dot absolute, and their method shortens the name of absolute to ABS, so that means absolute. So it's ABS, you can click there, and opening parentheses, because it is a function itself, so it needs a parameter. And now inside the parameter, you put this .x again. So this .x. And don't forget the semicolon, because it's a statement in JavaScript. And now we're just going to do this 2 more times for the y and z. This .y equals math dot absolute value of this .y. And then this .z equals math dot absolute value of this .z. And once again, we return this, which is the newly updated vector itself. Return this. Okay, I'm going to scroll this up once more. Oh, and I always forget the semicolon at the end of this function expression, so let's add that. Make sure I got them for all these. Yes, I do. It's one thing that I can't seem to remember, is putting a semicolon at the end of those function expressions. So hit enter a couple of times. And now remember earlier when we were talking about getting a vector's length. So let's add that now. Vector 3 dot prototype. And once again, we're adding to its prototype, so all vector 3s will have this functionality. Now, it would be nice to call this function simply length, but unfortunately for our naming purposes, the JavaScript programming language already has a built-in property called length that you can call on arrays. So we can't really use the word length here. So I'm going to use the full description and call it vector length in order to not have any conflicts with the JavaScript programming language. So let's call this vector length. Equals function. And once more, we don't need a parameter for this method because it's just going to take its own components and do the necessary calculations on those components in order to get a length, and then it'll just return that length back to you. So we can hit enter and then open curly brace and then enter. And now we're going to type out the famous Pythagorean theorem, which says that in order to get the length of a vector of any dimension, you just take its components, square them, and then add them together, and then you take the square root of all that. So let's write the square root first, because that's going to go on the outside of everything. So we call the math object again, so math. And this is a built-in math library in JavaScript that has the square root function. So, and that's denoted by sqrt. And there it is. You can see square root is a method. It's a function itself, so it takes the parameter. So we need to use the opening and closing parentheses once more. So opening parentheses, and then it says it takes a number. But now inside the use parentheses, we're going to put all of the calculations that we need to do on the vector. So it's going to be quite long, but I just wanted to start with this math square root first because that's going to go on the outside of everything. Now recall from the Pythagorean theorem that we have to square the components first and then add them together. So let's do sets of parentheses and we'll square the components and then we'll just add all those together. So let's do another set of parentheses. So opening, and it'll close it for you. And then inside those, you put this dot x times this dot x. And so we're essentially squaring the x component. So it times itself. Now go to the right past the first set of ending parentheses and type space, and then now type plus space. And now we're going to do the same thing with the y component. So we need another set of parentheses. So opening parenthesis, and it'll close it for you. And now do the same, this dot y times this dot y. Almost there, so one more to go. Now go to the right of that closing parenthesis and place a space and a plus again. And then lastly, we need one more set of parentheses. So opening parenthesis and this dot z times this dot z. So this dot z times this dot z. Okay, so now we have the complete Pythagorean theorem. So it takes the x component and squares it. It takes the y component and squares it. And it takes the z component and squares it. And then it adds all those together. So all of that will just return a simple number. It might have a fractional component or might not, but it'll just return a simple number. Then you take that number and you take the square root of that number. And again, that'll give you another number. And so you get back from this function just a simple number, a scalar number, which represents the length of the vector that you want to get the length for. Now I did forget something here. We need to add the keyword return because this function needs to return a value to be useful. So go right in front of the M here and type return and space. And now this is getting quite long, but I'm going to scroll over here, and this was actually a statement in JavaScript, so we need to add a semicolon to the very end of all this stuff. So go at the very end and add a semicolon. And once more, this is a function expression, so we need another semicolon at the end of all that. So there's a lot going on in this, but it's only a one-line function. So it returns the square root of all the components squared and added together. That's basically the Pythagorean theorem, written out in a way that the computer can handle it. And remember from earlier, the last topic we talked about was the normalization of a vector, which means you take the vector, which could be any length, and you shrink it or expand it so that it lies on the unit circle. And therefore, it will have a length of 1 exactly. So let's add that function now. I'm going to scroll up just a little bit and hit enter a couple of times. And now vector3.prototype once more. And let's call this normalize. Normalize equals function. And yet again, we do not need any parameters inside of these parentheses. So this normalize method is going to operate on itself. So hit enter and opening curly brace and enter. Before we type in the body of this method, let's go up here and add a variable that will be used by this method every time we call it. And so let's hit enter up here just one more time, and we use the keyword let to define a new variable in JavaScript. Let's call this new variable inverse length. And so I'll explain what that means in a sec. So inverse capital L to use camel case length. And we can initialize it to 0. It's simply a number. So what this is going to represent is to be able to normalize a vector, you first have to find its length, and then you have to divide each of its components by that length that you found. So let's say if you found a length of 5.7 or something like that, you would have to take the x component and divide by 5.7, and then the y component divided by 5.7, and then the z component divided by 5.7. And that will normalize the vector and make it unit length of 1 exactly. But the issue is when dealing with computers, it is oftentimes faster to do a multiplication than it is to do division. And so we want to avoid the case where we're taking x and dividing, and then taking y and dividing, and then taking z and dividing. It would be better if we had x times something, y times something, and then z times something. That'll operate a little faster on our computer, especially when we're doing this on every single pixel, which could be in the millions. So we could be doing this millions of times a second. So this variable called inverse length is simply going to get the length using our vector length function here, and then just setting it to 1 divided by that length. And so it's kind of like a fraction. So you put the number 1 in the numerator, and then you put the length underneath that in the denominator of the fraction. So it's 1 over length, or inverse length. So let's type that out and you'll see more clearly how this is going to work. So first we're going to get the inverse length of this vector. And so type inverse length, and we're going to use our variable now, equals 1 divided by, and now the cool thing is we can just call vector length on this vector. So use the keyword this, which refers to itself, dot, and then we're going to use our own method that we just created a moment ago called vector length. And so type vector length and it'll come up, and see it says it's a method, so you can just click there. And if you type the open parentheses, because remember it's a method or a function, so it needs parentheses. And it says it doesn't take anything in the parentheses, which is true. We didn't have any parameters when we created this function. So then you just type semicolon and you're done. So now we have an inverse length. It's 1 divided by whatever length we find for this vector. And now remember from when we were talking about normalizing a vector earlier, is once you find the length, you divide each component by that length. But in our case, now that we've done this the opposite way, we've done inverse length, we can multiply all the components times this inverse length, and that'll be a little more efficient on the computer. So let's try that now. So hit enter, and we're going to type this dot x times equals, which is much better in most cases for a CPU. And so times equals inverse length. And then we just do that 2 more times for the y and the z components. So this dot y times equals inverse length. You can hit enter when it pops up, semicolon. And finally this dot z times equals inverse length. And lastly, we return this, which is the newly updated vector. Return this. So by the time it gets here, the vector is now of unit length. So it has been squashed down, or if it was really small, it has been stretched out. But in any case, the tip of its arrow lies on that unit circle. Remember the purple unit circle that we had earlier? So now it's of unit length 1. And with that, we've accomplished what I wanted to do today, which was create a simple 3D vector library. And so if you look at the length of this file, it's only about 80 lines of code or so. So it's not that long at all, but it'll serve us well because when we write our future ray tracers in JavaScript for the CPU, we'll call on these functions every single time. So we'll use and reuse this little library over and over again. And so it's going to come in really handy, as you'll see in a moment. And wouldn't you know it, I just realized I forgot the semicolon at the end of this function expression. So let's add that. And with that semicolon, we are now finished. So as you know by now, if you've been following along, I always like to do at least a little graphics programming on each episode. And so let's create a small demo that uses our new JavaScript Vector3 library. So now let's go over here in the File Explorer and click on pixelloop.html. And now that we're in this part of the directory, let's create a new file. And this will be an HTML file for our demo today. So click on New File, and we'll call this rayDirections.html. So in a moment, this title will make sense. We're going to basically color the pixels based on the directions of their individual rays. So let's type rayDirections.html and then hit enter. And now click on Pixelloop once again and select all of the code, Control C, and paste it into rayDirections.html. Now right away, let's change the title so we don't get confused. So this is called rayDirections now. rayDirections. And likewise, go to pixelloop.js, which we were working on last time. And that's the matching JavaScript file for the last demo. And when you've clicked on that and you're inside this folder, click on New File. In a similar manner, we're going to make a JavaScript file that has the same name, but it ends with a JavaScript extension. So let's call it rayDirections again, but this time .js, which is a JavaScript file. And you'll see the little yellow JS come up here, and hit enter. And then go back into pixelloop.js and select all the code from last time. Control C, and go back into rayDirections, which is our new file, and Control V. We're going to reuse this code, but change it slightly for our demo today. Okay, at this point, I like to click out of all the old files that we're not going to use anymore. So let's click out of pixelloop.html and click out of pixelloop.js. And now you'll have rayDirections.html and then raytracingstyles.css, which is our style sheet that we'll use on every single project. And then our new file, rayDirections.js, which is the matching one to our rayDirections.html. And then the README, we'll update that in a minute when we do our demo. We'll update our GitHub repositories to reflect the new demo. And then over here we have mathutils.js, the JavaScript Vector3 library that we had just created. So if you program long enough, you'll encounter this mistake, and I've done it several times myself, so don't feel bad if it happens to you. But you have to remember to include this file, this mathutils.js, the new file that we created. You have to remember to include that into your projects. And so there's been many a time where I've created a whole library, and I was so proud that I've created this new library that I can use and reuse. And then I go to run the code and nothing's working. And come to find out that I simply forgot to say include that file in my project. So let's go do that now so we don't have that happen to us. So go into rayDirections.html. And right under this line, hit enter. And let's do a script tag. So we're going to include a new script. So left angle bracket, script, source, You can click on source there, and then it'll put the equals and the quotation marks in there for you. And now one of my favorite features of VS Code, we're going to type JS / and don't you just love it? So we're going to select our new math utilities library. So click on mathutils.js and it fills it in for you. And now we need the closing angle bracket, so right angle bracket, and it added the closing script tag for us. And I always like to push a little space right between these two, so hit space. And now we've officially included our new mathutils library. And so we can now use that functionality in our projects. One more thing we need to do is update this JavaScript file because it's still pointing to pixel loop, which was our old demo. So now let's point it to the new rayDirections.js file. So erase all this text in here and then type JS / and we get to use that great feature again. And now select rayDirections.js. Okay, so now at this point, I always like to double check and make sure everything's loading correctly and everything's working in the browser. So let's go ahead and run our live server now. So if this works correctly, we should have the demo from last time because remember, we haven't changed anything in rayDirections.js. It was simply a copy of our old project. We're about to update it, but for now, let's just see if it's working. So with the rayDirections.html and focus here, go down to the bottom right-hand corner. And in VS Code, I don't know why they make it this small, but it's really tiny. Find the Go Live button. It's way down here. And it says click to run live server. So click on that, and that'll open up your default browser. And there we have it. So we have our old demo from last time. So that means everything is working correctly. And now we can go back in and change our JavaScript code to use our new vector library, as well as create some new rays now that will go through each and every pixel. So let's go back into VS Code. So now let's go into rayDirections.js. And the first thing I want to add to this file today is the ability to update the display if the window is resized. So while your app is running, if someone resizes the window or maximizes it or is on a cell phone and they twist it from horizontal to vertical, then you need to be able to handle that and then redraw the screen. So let's add a function now that will take care of redrawing of the screen when the window dimensions change. Okay, first we can get rid of lines 11 and 12 because these no longer do anything. And instead, right there, we're going to add our window event listener. And we've done this before on previous episodes where we made a function that handles when the user changes the dimensions of the window. And so if this looks foreign to you, please go back a couple episodes and you can see how I do that, and I talk about it more in depth. But right now I'm just going to implement it. So window dot add event listener, and you can click on there. And now opening parentheses because it's a method. So, and then we want to listen for a resize event, and that is denoted by a string in JavaScript. So all strings have quotes, so we put quotes and it'll close it up for you. And then type resize. After that, type comma, space, and now we put the name of the function that we want to call when the window is resized. So I'm going to name it handle window resize. And now go to the end of the line and add a semicolon, because that technically is a statement in JavaScript, this add event listener. Now, we haven't defined what handle window resize is yet, so we're going to do that now on the next line. So hit enter and type function handle window resize, and it'll come up there. You can click on there. And now type opening parenthesis. And this particular function doesn't need any parameters, so we can skip this part and just go on to the next line and define the function. So hit enter, and then opening curly brace, enter. Now this function needs to update the canvas width and the canvas height. So let's go grab these lines, and we can cut these out. So Control X, and paste them in here. Control V, and now whatever the window's inner width and inner height is, it'll just place them back in canvas width and canvas height, and that'll update the display automatically. And don't worry that we removed it from here, because we're going to call this ourselves. We're going to call handle window resize and just kind of jumpstart the app, and so it'll do this canvas width and canvas height right at the beginning of the program when it starts up. Also, since these lines use the canvas width and the canvas height, let's grab those. So right below the let line here, so user info all the way down to this semicolon, Control X, and then click in here and put that below. And then maybe hit tab a couple of times on this line here just to move it over. This technically is one line of code, but it kind of spilled out. So if you follow it over here, it goes all the way over there. And that simply prints out the information about the canvas. So how many pixels is it wide and how many pixels is it tall? But we need to do that every time the window resizes, because now the canvas width and the canvas height are going to be different as well. And then scroll down just a little bit and go below where it says let be and hit enter a couple times. And now we're going to create a draw function. And so simply this will redraw the screen. So whenever the screen changes or you update one of the things in your ray tracer or something like that, you can simply call the draw function and it'll refresh everything and redraw the screen. So again, we type the function keyword and then just name it draw. And it won't take any parameters, but it still needs parentheses because it's technically a function. So opening parenthesis, and it'll close it, and then just go on to the next line. It doesn't need any parameters. And now opening curly brace. Now inside the body of the draw function, we can just put all this looping over the pixel stuff. So let's take everything from the comment here all the way down to the bottom of the file, including this semicolon, don't forget that. And now Control X and click in the draw function and Control V. And so now that placed everything inside the draw function. Now my VS Code didn't really format this correctly. This technically should be over one tab. So now do right click and then format document, and that'll correct all the spacing issues. So now we have a function draw that is a big function, so it goes all the way down to here. It's matching curly braces, opening curly brace to the closing curly brace. And now inside that big draw function is all the code to loop over all the pixels. So that goes from here to here. Okay, and now one final thing we need to add to handle window resize is actually call the draw function. So we need to redraw the screen. So click to the right of this semicolon, hit enter a couple of times, and just call the draw function. And remember how we do that in JavaScript is just type the name of the function with parentheses and then semicolon. So draw, opening parentheses, and it'll close it for you, and then type semicolon. And we can add a comment above that, so maybe hit enter here and 2 forward slashes, redraw the screen. Okay, so we just made a lot of plumbing changes to our demo now. So let's go back and check the web page and see if everything's still working. Uh-oh, we have a black screen and it says user text info. There's no info here. So something's not being called somewhere. So let's go back and check it out and see what we're missing. Oh, this draw function now handles all the graphics. And so we do call the draw function here, but we didn't call handle window resize where this draw function resides. So I bet if we change the size of the window, it'll automatically start. So let's see if that's the case. So I'm going to change the size of the window. Yes, as I suspected. So when you change the window, it kickstarts that handle window resize function, and then that in turn calls the draw function. So now if I change the window again, it'll update. Great. So at least that part's working. And you notice it recalculates the canvas width and the canvas height now. And so if you drag this around, it'll update the width and the height and the total pixels that it had to go through to create the final image. So we can go real small with it and it'll update like really fast. So it's almost instantaneous. And then we can go full screen again, and it'll take a while to chug through all those pixels. So let's maximize one more time. And now it's thinking, and then done. Okay, so everything's working as expected, but we need to jumpstart the app. So let's go ahead and do that now in the code. All we need to do is just manually call this handle window resize function. So go to the very bottom of the file after the draw has ended and click a couple times here, and now just call handle window resize. And when you start typing it, it should come up. Click on there, and it is a function, so it needs parentheses. And it doesn't take anything inside the parentheses. And now it's a statement in JavaScript technically, so we need a semicolon at the end. So semicolon. Now when we go back to our app, everything should be working. So yes. So now it started up correctly. And so now you can change the window size and it'll automatically redraw the screen and update all the canvas width, canvas height, and the total number of pixels it had to go through to generate that image. All right, so let's go back into the code. And I'll just add a note up here. So hit enter and then a couple of forward slashes, jump start the drawing of the screen. So that's where we manually call the handle window resize function. Even though the window hasn't been resized technically, we're just kind of jump starting it into action so that it'll force it to draw the screen for the first time. Okay, now at this point, now that everything's working, we're ready to use our new Vector3 library that we just created a moment ago. So let's go and scroll up to where we have the R and G and B variables, and maybe go under there, and let's create a couple of new vectors using our new vector library. So how about we call this one rayDirection? So rayDirection, which matches the title of this demo. And so this rayDirection is going to be a 3D vector that'll have X, Y, and Z components. So let's just create this using our constructor function. And that is done like this. So don't forget the new keywords. So you have to type new. And then now we can call our constructor function, vector3, opening parenthesis. And it reminds you that it needs a number for X, a number for Y, and a number for Z. So actually at this point in the program, we don't really want to set anything yet. So we're just going to leave it the default value. And it's going to default to all zeros. Because remember, we did that in our library to handle that case where you don't put anything in the parentheses. So just type semicolon at that at the end of the line. And just for fun, notice that colors also have 3 components. So they usually have R, G, and B components. And so there's nothing saying that the vectors have to just be little arrows in space. They can also be sets of numbers that have that many components. So R, G, and B, that's 3 components. And so we can make a color vector. So let's create an example of that. So let color vector equals new vector 3. And again, we don't want to initialize it just yet. We're going to do that in the main loop of this draw function here. So opening parenthesis and just type the semicolon at the end and leave it blank. So now we have 2 new vectors. We have a rayDirection vector that has X, Y, and Z, and we have a color vector that has also X, Y, and Z, but we're going to interpret those X, Y, and Z as RGB instead. And so there's nothing stopping you from interpreting the data how you want to. And I'll put a little comment to the side of this line here. So double / and then the X component equals the R color, Y component will equal the G color, and the Z component will equal the B color value. So essentially that'll allow us not to have to refer to these R, G, and B values as separate entities, but now all 3 color values will be contained in one nice color vector. Okay, now we're ready to make a ray for each pixel and then color the pixel based upon which direction the ray is pointing. So let's go inside these nested for loops here. And this is where we loop over all the pixels on the screen, no matter how many of them there are. And we were previously setting the pixel color based on where the pixel itself was located on the screen. But now we're going to give a ray direction for each pixel and then color it based on that. Before we do that though, I want to do just a couple of things to the coordinate system itself. And so if you notice, we have canvas x equals column divided by canvas width minus 1, and that puts everything in a 0 to 1 range, which is nice. And then canvas y does the same thing with the row of the pixel and then divided by how big the canvas is and the height minus 1. And that also puts it in 0 to 1 range. And then so here, I should add another comment here. Canvas y also goes from 0 to 1. So the problem though is that when we want to start adding cameras to our ray tracers in the future, it'll make the math much harder if we have 0 to 1 with the origin being in the top left-hand corner of the screen like it is now. So what we want to have is the origin 0, 0, or the center of the graph, you could think of it, as right in the middle of the screen. So 0, 0 is in this exact center, and then it goes out from there. Now because of that, it will go positive to the right and negative to the left, and then it'll go positive up and negative down. Also, one other issue that we need to address is the fact that the origin is up in the top left-hand corner, and that means that as you go down, the y values increase. But we want it to be like our graph that we saw on the previous whiteboards, where the value of y increases as you go up rather than down. So in order to do that, it just requires one line of code, and so I'm going to do that now. So you see where this canvas y is here. This is 0 at the top to 1 at the bottom. So we're just going to reverse that by making it 1 minus canvas y. And so that'll flip everything around, and then it'll go from 0 on the bottom to 1 at the top. And that'll make more sense geometrically, because that's how you think about most graphs, is that y increases as you go up the graph. So let's click at the end of here and then hit enter. And now we're just going to reset canvas y equals 1 minus canvas y. and end it with a semicolon. Now it just flipped it around, so now the 0 will be on the bottom and then the 1 will be on the top. But we still have the problem that 0, 0 is in the bottom left-hand corner now, and we want it to be in the middle. So how we do that is hit enter a couple times, and we're going to multiply all the values times 2 first. And so that'll take the 0 to 1 range and multiply it by 2. So now we'll have 0 to 2 range. And so I'll explain in a moment what we're going to do with that. So canvas x times equals 2. And then likewise canvas y times equals 2. So I'm going to update these comments now so they reflect what's going on in the code. I'm going to clip these. And put them here. Also, I'm going to add a comment above this line here. Flip y coordinates. So 0 is bottom of screen and 1 is top of screen. And now at this point, the canvas x goes from 0 to 1 and canvas y goes from 0 to 1. And now at this point, canvas x goes from 0 to 2. And the same goes for this line here, canvas y goes from 0 to 2. And so our final result that we want is 0, 0 in the middle, and then a radius of 1 everywhere. So if you go to the right of the screen, that's positive 1, and if you go to the left of the screen, that's negative 1. And if you go to the top of the screen, that's positive 1, and if you go to the bottom of the screen, that's negative 1. So if you think about it, the total width from negative 1 to positive 1 is actually 2 units. So you go negative 1 to 0 is 1 unit, and then 0 to positive 1 is another unit. So that's 2 units. And then likewise in the vertical direction, we have negative 1 at the bottom of the screen to 0, that's 1 unit, and then an additional unit to get to positive 1 at the top of the screen. So that's also 2 units in length. So we need a 2 by 2. And so now we do have a 2 by 2 screen, 0 to 2, 0 to 2, but it's 0 to 2 and 0 to 2. So what we need is negative 1 to positive 1 and negative 1 to positive 1. So we need to offset it. And the way to do that is to simply subtract 1 from this new range that we've created. So if you think about it, 2 minus 1 is 1, right? And if it's 0, 0 minus 1 is negative 1. So that puts us into the range of negative 1 to positive 1. So let's do that on these lines of code here. So canvas x minus equals 1 and canvas y minus equals 1 also. And now we can copy these lines and put them here, and I'm going to update those so they reflect what's going on. Canvas x now goes from negative 1 to positive 1. And likewise, canvas y now goes from negative 1 to positive 1. And I'll put in parentheses, this is left to right as you look at the screen. So left would be negative 1, and then right would be positive 1, and 0 is right in the middle. And then this would be bottom to top. And so bottom is negative 1, and the top of the screen is positive 1, and right in the middle is 0. And that's what we wanted. So that's the final result that we needed, so that 0, 0 is right in the middle of the screen, and now you have a nice one on each edge of the screen. And so you can multiply those times the colors, like say 255 or something, and that'll put the colors as being 0 in the middle to full brightness out on the edges of the screen, no matter where you go, left or right or top or bottom. And that comes in really handy when we want to add our ray tracing code in the near future, because we need the idea of where a camera is looking, and we want the camera origin and its view direction to go right into the middle of the screen and then to kind of fan out from there. Now that we have our screen coordinates all set up where 0, 0 is in the middle, we're ready to create a ray direction for each pixel. And so you might think that you could just create a new ray for each pixel, and that is totally valid, but that's going to put a lot of stress on the memory of your application. So think about it. If you go through all these for loops, that's like, maybe on some devices, that would be 1,000,000 times. And if you used let ray direction equals new vector 3, every time that moved on to a new pixel, you would do that operation about 1,000,000 times. And so that would be 1,000,000 new vector 3s. And so that's a lot of memory. And a better way is to create an object outside of the loop like this, ray direction, and just reuse it over and over again for each pixel, and just keep setting it to a different value each time you move on to a new pixel. So let's try that now. Let's take out the RGB code that we had before that was just setting the colors manually. So we can remove that. And now we can call the set method on our ray direction that we created. So ray direction dot set, and it's a function, so it needs parentheses. It says it takes an X, Y, and Z value. So to start off, how about we test out our coordinate system and make sure that everything's pointing in the direction that we think our coordinate system is. So let's set the X component of the ray direction to canvas X, and then the Y component of the ray direction to canvas Y. And that way, as it fans out from the middle, it'll create slightly a different direction for each ray. And so let's try canvas X for the ray directions X component, and then canvas Y for the ray directions Y component. And now this Z value here, we haven't really worked with that yet, because on the previous whiteboards, I was just working in 2D to be able to graph it and show you exactly what was going on. It's much harder to draw things in 3D. So on this Z component, let's just put in a hard-coded value now. And so we can mess with that in a little bit. So I'm just going to put -1. And the reason why it's negative is because the coordinate system, how it works, by the way, we're going to go over this in much more depth when we talk about cameras. So I'm going to revisit this idea of where the Z coordinate goes and what kind of handed system we use, like a right-handed or left-handed system. So we will cover all that in a future episode. But for today, just go along with me here. I'm just going to put a -1, and that simply means that it's going away from us. So we're shooting rays from our eye, basically, outward to the screen and then beyond the screen. So it's going away from us, and that's negative. If it was going towards us, towards our bodies, then it would be positive. And that's just the coordinate system that we're going to use. But I will explain all that in much more detail in a later episode when we start talking about camera placement and camera rotations and things like that. And that was a statement, so we end that with a semicolon. Okay, so at this point, the fill style needs a color, right? And so what we're going to do is visualize these ray directions by accessing their components. And so let's take our color vector, remember that we created up here, color vector, and we're simply going to copy ray direction. And then we'll put the color vector down here where it's time to draw the little pixel color. So on the next line, let's call color vector dot copy. and that's a function. It needs parentheses, and it says it takes as a parameter another vector. So let's put rayDirection in there, our rayDirection vector, and that's a statement, so end that with a semicolon. So now color vector will be whatever rayDirection is. The two will match exactly now. And so before we do any more with this rayDirection, let's just print out these colors on the screen. And so just to make sure everything's working. But just up front, there will be some issues that we'll have to fix, but we can do those easily. And I'll show you how to do that in a moment. But let's just go ahead and print out the colors and see what happens. So instead of the R here, all you do is call color vector, and you access its X component, which can also be interpreted as an R component, so a red color channel. So color vector dot X. And so even though it doesn't say R, it says X, we're just interpreting it to be a color instead of a direction. And then likewise do the same for G, so that'll be color vector, and then the next component, which is Y, so dot Y. And finally, then erase that B there, and then type color vector dot Z. And that will be interpreted as a blue color. So now we have color vector X, color vector Y, color vector Z. And essentially that means we're going to interpret that as an RGB triplet. So R, G, and B. And now it'll color each and every pixel on the screen based on which way the ray is pointing. So it should be dark in the middle because we have canvas X and a canvas Y of 0 right in the middle. And as it fans out to the edges of the screen, it should get brighter because that gets to 1. Now we will have a problem, like I said, because it's going to go -1. And remember, the Canvas API does not like negative values. So that doesn't make sense to have like negative red or negative 255 or something like that. So we're going to have to rectify that in a minute, but let's go and see what it looks like on our screen. Okay, so it's still working because we have the correct information down here, but we're getting all black pixels. So that tells me that something is not scaled correctly, and we may have some negative values to deal with. So let's go and see if we can start coloring these pixels where it makes more sense, where they're put in a range of 0 to 255. So, oh, I see the first problem. We didn't multiply it by 255. So all the pixels are like 0 to 1 or -1. So when you put that in color space, it's only a 0 and 1 in color space out of 255 values of brightness. So everything's black or really dark shades of black. So let's scale these up now. And do you remember how to scale a vector? So we're going to call multiply scalar. So color vector, multiply scalar. We knew this function would come in handy, right? When we were writing our 3D vector library. So let's just multiply everything by 255 and see what happens. Now if it's 1, it'll be full brightness, 255 in that channel. And then if it's -1, it's going to be -255. So we are going to have to deal with that in a moment. But that'll be super easy. I just want to see what this does. So let's go and see now what we get. Oh, cool. All right, we're getting there. So now we have a bright green up here and a bright red over here. So that tells me that the values go up as we go up the screen. And that's what we want. Remember, the Y was going up as you went down the screen. And so that was backwards to how most people think about the Y coordinate. So now we at least have the green getting brighter as you go up. And in a similar way, the right side of the screen is where it's getting brighter in the red channel. So that's great. And at this point up here, both the red and the green channels are full intensity, and so you get red and green full intensity, and that equals yellow, or bright yellow. So that's correct up here. But now this should be dark here, but now we have a problem. This over here on the left bottom corner and the left side of the screen is all black. And so I have a feeling that that's because of our negative numbers over there. So just to be able to color this correctly, we're going to have to temporarily disable all those negative numbers. And so how do you do that? Well, you just take the absolute value, right? So let's take the absolute value of all the rayDirections. And that's why we wrote that little absolute value function for our vector library a moment ago. So go back into VS Code. And now, before we multiply this scalar, let's add a line in here where we take the absolute value of the color vector. So color vector dot absolute. And that is a method, so it needs parentheses, and it doesn't have any parameters, remember, so it just operates on itself, and it changes itself, basically. That was a statement, so semicolon. And now we'll have 0 to 1 when you go to the right, and then we'll have 0 to 1 as you go to the left side as well, because all those negatives will be turned to positives. And so we should have an equal amount of color on both sides of the screen now. So let's go check. All right, cool. It's working. So as you can see, it's really bright up here, and then we have a bluish color in the middle, and then it gets really bright at the bottom again. And now on the right side, it gets really bright magenta color on the very right. And then on the very left, it mirrors that exactly, and now does the correct coloring, which is the bright magenta color. So now the left and the right match, and the top and the bottom match. So now we're doing much better. We have the notion of 0, 0 being in the middle, and then as it fans out from there, we get wider and wider, and it gets brighter and brighter. So our rays are doing the correct thing for each pixel. Oh, and by the way, this blue color came back because remember we had a -1 in the Z component, which is blue of -1 times 255. And that doesn't make sense in the Canvas API. So rather we took the absolute value of everything and that turned it into a +1 for the Z component of the color vector. So now it's +1 times 255, and that equals a bright blue. So that's why we see blue most everywhere. And like we did on the previous episode's demo, we need to make this final number a pure integer. So as of now, when you multiply it and you do all this stuff to it, the color vector may have fractional components. So it might be like 3.625 or something like that. So we need to chop off the 0.625 and leave it with just a pure integer 3. And the Canvas API likes working with whole numbers like that. So that's why we wrote that function in our JavaScript vector3 library that floors the values of the components down to the nearest integer. So let's call the floor function now on this color vector. So we simply call color vector dot floor. And then it says it's a method. So it needs parentheses. And it doesn't take any parameters, so you just leave it blank. It operates on itself. It changes itself, basically. And so type a semicolon, because that's technically a statement in JavaScript. And now we should have pure integers for all the colors on the screen. Now, if you go look at it, it won't make a difference, but it will be slightly more efficient because the Canvas API won't have to go through all that data and chop off all those fractional components. We've already done that. And then we just feed it pure integer numbers. And so it'll operate a little faster with those whole number integers. And one final function we can call today is the normalize function. So remember, we have a rayDirection for each pixel on the screen, and it's based on where the canvas X is at that moment, and then where the canvas Y is at the moment for that pixel. and then a hard-coded value of -1. So this will definitely not be a unit vector when we loop over all the pixels, because these numbers will be varying quite a bit as you move from left to right or bottom to top. And so what we would like is to normalize all those rayDirections, and so they all have a unit length of 1 exactly. So click after this line here and then hit enter, and right below the rayDirection line we call rayDirection again dot normalize. And you can click on it if it pops up here. And again, that's a function, so it needs parentheses. So opening parenthesis, and it'll close it for you. And it says no parameters are needed. And it basically operates on itself and then shrinks itself down so it's exactly 1 in length. So type semicolon at the end of that. So in your mind, if you can picture this, we have a ray starting. Now, we didn't really specify ray origin, and we will in the future, but for now, the ray origin is just assumed to be 0, 0, 0. So all the rays start from our eye or our body, if you want to think of it that way, or our head, and then they all go through each pixel. So the first pixel is at the top left-hand corner of the screen, and so it goes from your eye to the top, it's backwards here, so top left-hand corner of the screen. And then the next pixel, and then the next pixel's ray, the next ray, the next ray, and then it goes all the way to the right. Then it goes down 1 row and does that same thing over and over again. And then it continues all the way down to the bottom of the screen, where it shoots a ray towards the bottom left-hand corner, and then passes the middle point, and then bottom right-hand corner, and then we're finally done when we get to the bottom right-hand corner. So if you can imagine all those little rays starting at your eye, going through each pixel, and then out like that. What we want to have, though, is mathematically, it helps to have all those directions as being a length of 1 exactly. So we're taking all those long rays and we're just kind of chopping them a little bit so that it goes exactly 1 unit of distance from your eye. And that's what we're doing with this one line of code here. So let's go look at the result on the web page and see what that looks like when you normalize something. Well, actually, to tell you the truth, not much difference, right? So it is a little dimmer at the edges because remember, we were going outside the boundary of being a unit length vector. But honestly, I can't tell much difference between the non-normalized and the normalized version. But it's just good to know that we have all those directions in a normalized state so that they're all 1 exactly in length. And that'll allow us in the future to do operations more easily with those unit length direction vectors. So the final thing I wanted to do with this visualization is change the value of the Z component or the B channel. So this is, remember, R, G, and B. Basically, we're interpreting it that down here as R and G and B. So let's try a value less than 1. So how about negative 0.5? And let's see what that looks like. Oh, interesting. So just by changing the blue channel or the Z component of all the rays, so in other words, the rays X and Y components are exactly the same. They're still fanning out like this, and they start at 0, 0 in the middle of the screen. And you can kind of see that, but now we have a little less blue. So we have it was 1 in length before for the blue channel, and now it's only 0.5. So it's much darker and it's much smaller. So the blue is less dominating now as you go out to the edges of the image. Let's try an even smaller value. So 0.01. Oh, that's kind of cool. So now the blue channel is almost non-existent because it's at its highest, it's 0.01 in magnitude for that Z component. And so if you were to zoom in on this pixel, I bet you would see a blue pixel, but it's really tiny. So let's make it a little bigger so we can see it. How about 0.1? Okay, that's better. So now we have the blue is right in the middle of the screen. So it's in the middle going top to bottom, and it's in the middle going left to right. This kind of looks, it's interesting because it kind of looks like you're looking down a long hallway, and so you have a green ceiling and a green floor, and the walls are red. So the left wall is red and the right wall is red also. And then you're looking into the void here, which is kind of like a twilight blue color. So actually this is kind of cool. So I'm gonna leave it like this for today. And so now the final thing I want to do is upload our new vector library and our new demo up to our GitHub repositories. And so if you've been following along with me for these last few episodes, you know how easy that is. It's just a couple of clicks of a button and it's up on the cloud where everyone can enjoy it and everyone can see your demos and they can view your source code and see how you did it. So we're about to see that in action yet again. So let's do that now. Oh, one more thing before we do that real quick. Let's go into the README file and add a quick link to our new demo so that when people visit your online repository on GitHub, they can easily click the link for the demo and it'll just pop right up. So let's go to the readme.md file and just select this text here and copy it below. So Control-C, Control-V. And now we named our new demo rayDirections. So change pixel loop to rayDirections, capital D. rayDirections. And now this text here is what they'll see when they go to click on the link. So let's change that to rayDirection. How about visualizer? That sounds kind of cool. Okay, and then let's change the description so you can erase this text here. So I just typed here a short description of what this demo does. So using our new Vector3 library assigns a unique rayDirection vector to each pixel. The RGB colors represent the rayDirection vector components. So red is X, green is Y, and blue is Z of each pixel. Now if you look over here on the left side of the screen, you see the source control icon, and that has a notification that 4 files have changed. And so we have Matthew Tills has changed, or we've added Matthew Tills, we've added rayDirections, we've added rayDirections.html, and we've changed our README file. So that's 4 new things that have happened with this repository. And so now click on the source control and let's add a commit message. So in the text field here, put added new vector 3 library / new rayDirection demo. And I kind of shortened this direction here because the commit descriptions should be nice and short. Okay, and now we get to use one of my favorite features of VS Code, and that's the direct integration with your GitHub repository in the cloud. And so all you have to do is click commit, and now you just click this purple button, sync changes, and that'll immediately push all of our changes up to the cloud. And so our repository on GitHub will reflect exactly what we've done here today on our local machines. So I think that's really cool. So click sync changes. And just in a couple seconds like that, it's done. And so now people can go and check out your new demo and see the source code to how we implemented our vector3 library, as well as how we changed the screen coordinates and how we visualized the rayDirections as RGB colors. Well, once again, we did a whole lot today, so I hope you enjoyed all of the new topics that we learned about on today's episode. First, we learned about vectors and what they are and how you can do simple operations with vectors. And then we learned how to use those vectors to represent rayDirections in our ray tracers. Next, we created our own vector3 library in JavaScript. And now that we have that library at our disposal, we can call upon it for our future ray tracing projects. And finally, we learned how to visualize rayDirections by coloring each pixel on the screen based upon where its rayDirection was pointing. And so on the next episode, I'm going to go back and fill in the gaps of a vector product. And in particular, we'll look at the first type of product, which is called the dot product. Also on the next episode, we're going to take a look at how to intersect a ray with a plane. So by the end of the next episode, we'll be able to raycast against a plane and visualize that plane in 3D. So I'll see you on the next one.